Now we want to take the hyperbola a little bit further and look at one of the particular situations. Now this is the case if we have a right angle between our asymptotes. So we've got our hyperbola. Let's take that. Our hyperbola there, and we've got our asymptotes. What if they start to meet at right angles? If that's the case, then we'd have this relationship: b on a times minus b on a would be equal to minus 1. We take their gradients, multiply and they give you minus 1. So we get minus b squared on a squared is equal to minus 1. So a squared must equal b squared, or a is equal to b. What does that mean? So if a is equal to b, we get this type of hyperbola. So where x squared minus y squared is equal to a squared there. So because b squared is on a squared, so the asymptotes are actually the lines y is equal to plus or minus x. Now what does that do for us? Well, if b squared on a squared is equal to 1, we get our eccentricity must be root 2. So whenever we get an eccentricity of root 2 for our hyperbola, then we have what we call a rectangular hyperbola. So because it's a special one, because the asymptotes are meeting at right angles there. So we have this situation, it's at right angles, so the the eccentricity is going to be root 2, so we have what we call the rectangular hyperbola. Now what does that look like? Well, if we take our rectangular hyperbola here and take our asymptotes, and if we move the asymptotes to become the axes. So we take these and rotate them 45 degrees. So if we have that situation, so take it, rotate it 45 degrees, and create new axes, which we'll call capital X and capital Y. Then we have our hyperbola looking like that. Now, hopefully you're looking at that going, wait on, that's the hyperbola we use all the time. And that's what we've generally called just a hyperbola. But really it's a rectangular hyperbola. And that's the one we use a lot in the junior school, and when we're looking at courses there in the 2 unit and extension 1. So we have our new hyperbola, and our axes have been translated there, and this hyperbola can be put into that form: x times y equals some number, which we can call c. We'll call c squared. So the rectangular with the major axis of length 2a has that equation. So that's what we're seeing there. The major axis has that length there. So there's all the relationships that exist. So the parametric equations for this one, so if x, y is equal to c squared, then ct times c on t would satisfy that and become the parametric equation. So that's the parametric equation. X is equal to ct, y is equal to c on t. And as you say, you can just multiply them, that will give you c squared. So that will work for us every time. So how do we start to use this? We'll find the equation of our chord. So x1, y1, x2, y2 are 2 points on the rectangular hyperbola. X times y is equal to c squared. So to get our equation, we need our gradient. So we've put our functions in. So the difference in the x values, sorry, y2 minus y1, and because y1 and y2 can be written like that, that's why we can write it like that there. And then we get divided by the x2 minus x1 there, and then we start to manipulate this, get our common denominator of x2 minus x2 x1, and multiplies by x1 multiplies by x2, we get the minus c squared x2 minus x1, so they can start to cancel, and there's our gradient of our function. So that's where we're able to do that substitution into that part. Finding our equation, or y minus y1, the c squared minus c squared on x1 x2, a gradient x minus x1, multiplying out by x1 x2, and then we start to manipulate our terms. And notice we've got the x2 x1 x2 and y1, which, remember, y1 we said could be c squared on x1, so the x1's cancel, and that's where you get the c squared x2, c squared x1, and there's our equation of our chord. In parametric form, we do the same thing with Cp, C on P, CQ, C on Q, so just two different values of the t that we saw there before, and we're able to manipulate, get our gradient, and get 1 on minus PQ as our gradient, substituting the equation of the line, and then we're able to expand out to get that equation for our chord in parametric form. Equations of tangents. So we got the x1, y1 on the rectangular hyperbola, and so to get our gradient, well, we need to multiply x times y equals c squared. So you can put that as a explicit function, but if we differentiate it implicitly, we'll get dy dx is minus y on x, which gives us a gradient of minus y1 on x1, so we can substitute that in. So we multiply, and we put that in with x1, y1, and then multiply through by x1, and we collect our terms, and we'll end up with two lots of x1, y1. Now remember, x1, y1 lies on the hyperbola, so if we substitute it into that, it should satisfy and be equal to c squared. So that's where we're able to go from x1, y1 equal to the c squared there, and get two lots of c squared. So in parametric form, CP and C on P are our points. So our gradient there, we said before, was minus y on x, so we substitute and we get minus 1 on P squared. So we do the substitution with the point, multiplying through, and we're able to clean it up to get down to that form. With the equation of the normal, so our gradient of our normal would be x1 on y1. So again, we substitute it in with our point x1, y1, and then collect our terms. And we get the x and y's on this side, our constants on the other side, and that's as simplified as we can write that equation. So in this case, we'd have CP on C on P for the parametric form of the gradient, which gives us P squared, and then we put that in and multiply through by the P to start to get rid of the fractions, collect our x's and y's on one side and our constants on the other. So there's our equation of our normal in parametric form. And then the chord of contact for the tangents from external points. So if our external points x0, y0, and points at P and Q meet there, we're going to get the equations of the tangents there. So x y1 plus y x1 is equal to 2c squared, x y2 plus y x2, 2c squared. Now again, because those two tangents meet at t, which is x0, y0, we can substitute. So tp, when it goes through there, we get x0, y1 plus y0, x1 equals 2c squared. And then when the point at Q goes through t as well, we get the x0, y2, y0, x2. Now notice x0 and y0 are common to both those, as well as the 2c squared. So they're in that same form. So really, the y1, x1 satisfies that equation, and x2, y2 satisfies that equation, which means that must be the equation that the lines P and Q, the line PQ, goes through. So that chord PQ goes through that, has that equation because it goes through both those points and satisfies those 2 points at the same time. So that's a similar proof to what you've done with the chord of contact of tangents with the parabola, with the parabola in extension 1 parametric form, as well as the hyperbola and ellipse as well. So have a look at all those. Remember those proofs. Be able to manipulate them using all those techniques we've used before. It's very similar to the work we've done with the hyperbola, except that we're just dealing with x, y is equal to c squared in this case.